Have you looked at our roads lately? Seriously, if you've driven on a highway or crossed a bridge recently, you absolutely know the story. Cracks, potholes, and just endless repairs. You see, modern steel-reinforced Portland cement structures are engineered to be lightweight and handle massive bending moments, which is great, but they frequently start deteriorating within just 50 to 100 years. Now contrast that with ancient Rome. Structures like the Pantheon, with its massive unreinforced concrete dome that's literally 6 meters thick at the base, have been standing strong for over 2 millennia. We're talking surviving earthquakes, volcanic eruptions, and incredibly harsh marine environments. It's a crazy disparity. How on earth did the ancients build things to last practically forever, while our modern marvels crumble in a single lifetime?
Today, we're going to put on our detective hats and solve a 2 millennia-old engineering cold case. We're going to uncover the completely forgotten chemistry of ancient Roman concrete and discover how this incredibly resilient material from the past might just hold the key to solving some of our most pressing modern climate crises.
Okay, let's dive into this. Here is our roadmap for today. First up, the Roman concrete mystery. Second, unlocking the hot mixing secret. Third, how Roman concrete heals. Fourth, the marine concrete phenomenon. And finally, ancient science, modern solutions.
Let's start with Section 1, the Roman concrete mystery.
For the longest time, historians and engineers just wrote off Roman concrete's survival as survivorship bias, assuming we only see the ones that didn't fall down, or they just got pure luck with some magical volcanic ash. But the real clue was actually hiding right in plain sight. There are these tiny millimeter-scale white mineral chunks called limeclasts. And amazingly, conventional civil engineers completely dismissed them. They literally assumed these white chunks were just evidence of poor craftsmanship, that Roman workers were just sloppy and failed to mix their mortar adequately. Sloppy? The Romans? This totally contradicted their highly standardized construction manuals. Well, it turns out modern engineers were dead wrong.
The truth was finally proven by a massive archaeological breakthrough late in 2025 at an active, unfinished construction site in Pompeii. This site was perfectly frozen in time by the eruption of Mount Vesuvius in 79 CE. By carefully analyzing the raw material piles, researchers found intact quicklime that was pre-mixed with dry volcanic ash. Using stable isotope analysis, which is basically a highly precise chemical fingerprint, they traced the carbonation profile and proved definitively that the Romans were not using traditional wet, slaked lime paste. Nope, they were using a highly standardized dry pre-mixing technique across the entire empire.
Moving on to Section 2, unlocking the hot mixing secret.
So, to really grasp that Pompeii discovery, we've got to look at the actual thermochemistry of what happens when water hits that dry mix. This equation right here is essentially an ancient recipe for a massive, highly exothermic reaction. When water is introduced to that dry, pre-mixed pile containing unslaked quicklime, it triggers an instantaneous thermodynamic event. This localized heat is intense, quickly raising the overall temperature of the paste to over 80 degrees Celsius. And this extreme heat does something truly magical. It instantly evaporates the surrounding pore water. That completely arrests the dissolution of the quicklime particles, securely trapping these highly reactive calcium cores right inside the setting concrete.
And those trapped cores, those are the limeclasts. They aren't mistakes at all. They are highly reactive calcium reservoirs, featuring a uniquely brittle, micro-cracked, nanoparticulate architecture. Think of these limeclasts as little, functional first aid kits, intentionally distributed throughout the entire structure, just waiting in hibernation for future mechanical failures to occur.
Which brings us to Section 3, how Roman concrete heals.
Okay, so here's the absolute genius of it. How do these little first aid kits actually jump into action when the concrete sustains damage? Let's walk through the autogenous or self-generated healing loop. When mechanical stress or thermal expansion causes a microcrack, that crack naturally wants to follow the path of least resistance. Because our limeclasts are exceptionally brittle, the cracks preferentially travel straight through them, ripping them open and exposing a massive, concentrated surface area of reactive calcium. Then, environmental water, like normal rainwater, enters the crack. But instead of rusting and ruining the building like it does today, the water dissolves the calcium. This creates a highly saturated solution that actively migrates through the crack via capillary action.
And this brilliantly illustrates the genius of the design. That dissolved calcium reacts with carbon dioxide or carbonate ions naturally present in the water, triggering the rapid precipitation of crystalline calcite. Laboratory tests utilizing this exact hot mixed method showed that a 0.5 millimeter crack can be completely sealed in just 14 to 30 days. The water flow literally just stops completely.
And get this, the Romans didn't let anything go to waste. Any excess calcium hydroxide that doesn't immediately form a gel to bind the crack doesn't just sit there doing nothing. Over time, it undergoes slow carbonation upon contact with atmospheric carbon dioxide, converting into even more crystalline calcite. The concrete is literally using the surrounding environment to continuously reinforce its own structural integrity. It's incredible.
Let's pivot to Section 4, the marine concrete phenomenon.
Now let's take a trip to the coast. While architectural concrete heals via that calcite recrystallization we just talked about, Roman marine concrete, the stuff used in their massive breakwaters and harbors, reacts to the ocean in an entirely different, highly complex way. Because these structures were so massive, the combined heat of hydration essentially slow-cooked the concrete core. It created an adiabatic curing environment, basically acting like a giant self-heating thermos, baking at 85 to 97 degrees Celsius for up to 2 full years. This triggered an absolutely incredible diagenetic or rock-forming process.
The ultimate payoff of this centuries-long immersion in seawater is represented by this incredibly rare crystal, aluminous tobermorite. Instead of saltwater degrading the structure over time, the highly alkaline pore fluid constantly dissolves glassy components from the volcanic ash. Over centuries, reactive silicon and aluminum ions bond with dissolved calcium to grow this deeply interlocking crystal. Essentially, it acts like a chemical sponge. Aluminum ions swap in and create a negative charge that literally locks onto sodium and potassium from the seawater itself. The result is a structure with an exceptionally high bulk modulus that is constantly actively reinforcing itself against crashing ocean waves.
And finally, Section 5, Ancient Science, Modern Solutions.
So what does this 2,000-year-old chemistry have to do with us today? Well, to understand the urgency, you have to realize that modern ordinary Portland cement production is kind of an environmental nightmare. It is responsible for a staggering 8% of global anthropogenic carbon dioxide emissions. 8%. The modern world relies heavily on concrete to function, but the way we make it right now is fundamentally unsustainable.
And what's really interesting about this is the massive difference in manufacturing requirements. To produce modern Portland cement clinker, you have to heat clay and limestone to a massive 1450 degrees Celsius. That requires a huge amount of fossil fuels. But Roman concrete? They calcined pure limestone into quicklime at just 900 degrees Celsius. That's roughly a third lower than modern requirements. That drastically reduces thermal energy demand while simultaneously building in those active, autogenous repair mechanisms that modern cement simply doesn't have.
Enter deep tech startups. This is where the application becomes genuinely impressive. A company called DMAT, which was actually founded by researchers who study this ancient chemistry, is translating it directly for the modern construction sector. They've engineered a proprietary active additive called D-lime that perfectly replicates the brittle nanoparticulate architecture of Roman lime clasts. And to make it globally scalable, they figured out how to replace that rare Italian volcanic ash with widely available calcined clays, ensuring the whole mix is completely compatible with modern automated pumping equipment.
The real-world benefits of bringing this commercialized ancient science to our modern highways and buildings are massive. By cutting back on energy-intensive Portland clinker, these Roman-inspired mixes deliver a 20% baseline reduction in CO2 emissions right out of the gate. They also reduce the carbonation coefficient, which protects the internal steel rebar in our modern buildings from rusting. Furthermore, these self-healing mortars yield up to 30% in cost savings, all while boasting 3 times the tensile strain capacity of conventional mixtures.
And the financial stakes? They're an absolute game changer. Corrosion and cracking in reinforced concrete structures cost the global economy more than $100 billion annually in maintenance and repairs. By introducing self-healing technology directly inspired by the ancient Romans, we can fundamentally extend the lifespan of our infrastructure and drastically slash those life cycle costs.
The Romans engineered a material that didn't just resist its environment. It actually used water and carbon dioxide to actively heal and strengthen itself over millennia. It's a profound shift in how we think about building our future. If a 2,000-year-old recipe for concrete can drastically cut our carbon emissions and save billions in modern infrastructure repairs, it leaves us with a thrilling question. What other forgotten ancient technologies hold the key to solving our modern climate crises? Thank you for exploring this mystery with me. Keep wondering and keep looking to the past to fix the future.
What the Fact? Follow for more.